So I'll be talking about two topics today. The one topic is on the concept of lambda, and the other one is generator functions. We are now coming to slightly advanced functions territory, and lambda are used where small functions are needed. Generator functions are not used a lot in day-to-day work, but I use them in different situations. So I'm going to talk about these two things. And there are a few function topics which I will be covering towards the end in the advanced topics. So we can look at those topics in the end. So let's get started with the lambda. So lambda, we have talked about functions in general. Let me open the IDE. We have talked about functions in general in which we define a function using a def. Right? What that does is it creates a function definition and creates a code object and gives it a name, whatever name we're gonna call it. So suppose, just quickly say, so suppose you have def and you can say function one, it takes some arguments x comma y and return x plus y. Suppose you have this function, right? So this is one way of creating function. There is another way of creating a function, and there is a difference. There's a fundamental difference when the functions are created the other way, and I'll tell you what the difference is now. The other way to create a function is by something called lambda. And I think it's taken from which programming language? I can't remember. This is literally taken from Lisp. I think Lisp. Yes, it's taken from Lisp programming language, and they exactly use the same name. So essentially, when you define a function with lambda, let's say you're going to say x comma y. So these are the arguments. So you'll say argument one, argument two, dot dot dot. Let's say argument n. Then you put a colon, and then you will do something with an argument. You write one expression with these arguments. Suppose it is like argument one multiplied by argument two plus argument three. You write one expression. You don't return anything, nothing is done. So basically, just by taking these arguments, this operation is performed and the answer is returned. Let's create a simple lambda to try this out. I'm going to use the terminal window to try this. So let's create a lambda. Suppose I'm going to say lambda x is equals to, let's say, 10 multiplied by x. And that's it. This is how you define a lambda. This is the argument, and this is the expression is the return value itself. You can assign this lambda to something. You can say f is equals to this lambda. Now you will call f the similar way how you call a function. Since this function itself doesn't define a name, this is called an anonymous function as well. You are literally assigning a function to another function in this way, and then you're calling it. The fundamental difference between, a lambda and a normal function is that, just one second. Yeah. Lambda is basically can be used wherever an expression is used. So suppose you have, let's say, a list. All right. And suppose you want to create, let's say, a list of functions. Then in the list, let's say you want to define some basic functionality, then essentially you can just put this definition here. You can say, let's say lambda of x square. Suppose this is the first lambda. And let's say the second argument, the second value in the list is, let's say, and let's put one more. So when you look at this list, you will notice that the list is actually 3 functions now. If you do list of 0, then that is a function. If you want to call that function, then essentially you can call it with some argument. Or you can write a loop on this list. You can write for function in list function of 10. When you do that, you will get the answer. So essentially you're able to put this anywhere where you're able to define a function essentially anywhere where an expression can be put. So this gives you some flexibility in defining very short functions, right? Functions which are not going to be used apart from where they are declared. And I mean, and essentially you don't want to keep the definition and the definition and use far away. So you can just define them right there. Lambda can also be used as the key argument in our sorted function. So the sorted function that we have been using, you can instead use lambda as well. But first I'll give you some time if you want to try this out. Take a minute, try this out. And if you have any questions, you can ask me. So suppose you have, let's say, a list of strings. Okay, suppose you have a list of strings, something like this. A, and then you have BPP, CC, and let's say D. Right? If you write sorted of S, then you get this answer. Right? But let's say if you want to sort this based on length, then you have to use something like, say, a key function, key equals to len. You get a different answer this way. Once again, let's define this again, and let's try some things out. Let's say we want to sort based on the last character. We have done this example in past as well. Right, so suppose you have, this is last character is W, X, and Y, and Z. At this moment, if you say sorted of S, then the list is already sorted. But if you want to sort based on the last character, then there are two options. You can define a key function. You can write def key, which def, let's say a key function, which is, let's say, is called last. It takes in an argument and it returns the last character. So then you can also call this sorted. Just give me a second. Let's name this properly. Then you can define the sorted function based on this. You can say sorted of L, where key equals to last. What did I do? None type and none type. Really? Where? How come this is none type? Last of. Oh, my mistake. I'm so sorry. When I defined the function, I did not return anything. I need to return something from the function. So there's nothing to compare. That's why it's returning none and there's no way to compare. I think it should work fine now. So this is the function. And once again, we come here and you notice that now we are sorting based on the last character here. right? So instead of defining this last function separately, you could have written a lambda here as well. You could have just write lambda of, let's say, some argument x, and once again you don't return anything, you just write x of -1. That is the value supposed to be returned. So now notice the result is still the same. So this saves you some effort. You don't have to define this function, which was just defined for this, for the purpose of this sorting, and it only existed, there was only one use, and it's somewhere further away in the code, versus you can just define the whole logic right here. So you can do that. Okay, I'm going to give you a minute to try this out yourself as well, and if you have any questions you can ask me. Let's talk about the next topic, which is the generator functions. I use them at times, and I'll show you some test cases, use cases where this works. So what is a generator function? Let's define a function real quick, and we'll come to generator functions. Functions.py. Okay, let's define a function called, let's say, squares. You give squares an argument n, and what this does is basically it generates the values, it generates the squares of all the numbers till n, and it returns those. So suppose I'm going to create a result, and for x in n, essentially result dot append x to the power 2 and return result. Suppose you have this type of function, okay, and you called squares of, let's say, 10, and you print that. So we run this. What am I doing today? What happened for x and n? Oh, my mistake.
Use the range.
I'm just, okay. Let's do this. So there you go. There are your, this is the return list, right? Suppose you have a big thing like this. So you can return, so what you have to do is you compute the whole result and then you return it once. This function becomes a generator function, which I'll explain in a second what that is. If you just change this, instead of, let's say, doing this, you don't need to do this in this particular case, and just change this to, instead of returning, we just write yield. So generator functions can return multiple times. And they become very useful in certain situations. So suppose you have this function here, okay, and you're going to say, let's say, x is equals to squares of 10, and you write print x. So when you do this, what you get back here is not a value. You have gotten something called a generator object, which is squares. So here, what this does is that instead of uh, returning a single value, you get a generator function back, which is an iterator itself, on which you can iterate. So let's write a very simple function here. So let's say func of, let's say, n, and what this does is for x in range of n, yield x, because this will be easy to do this. So I'm going to say f is equals to func of, let's say, 10. So this f is now a generator object. If I write next of f, it will generate 0. So this function internally is keeping track of where it is. And every time it encounters the yield statement, it returns that value. Now the function is halted. It is not doing anything. When we write the next again, then it knows that the x is at 1. So it needs to return that x. If I do this again, it will be 2, 4, 5, and at some point of time it's gonna run out of it, and basically you're done. So if I take this function again, let's take this and copy this here. So if you call this function, for example, and you call it with, let's say, func of 5, oh sorry, squares of 5, then this will return a generator object. Suppose you wrote gen equals to that. So now this generator function, if you call it next on it, then essentially this function will begin the execution for the first time. It will say, okay, this is a generator function with 5 value. So now you're going to write a loop and say for x in range of 5. So the first value of x is 0. Yield x square. So this function will return 0 square back, and it will halt. So the function is going to remember its value. So now there is a function object called gen, which is pointing to square of 5 somewhere. And internally, it's keeping track of its variables. It knows that x is at the moment 0. And it's on, let's say this was line number 1, 2, and 3. So it's on line number 3 right now. So when you say next of gen, this will continue again. And now x becomes 1, and this function will return 1 square, and it will halt. The next is the same thing that is used in the looping as well. The same tool that gets used in the looping. Suppose you have a string s is equals to Saturn, and let's say you create an iterator object on this, right? So if you have, let's say, this called x, then you write next of x, you get this. You can make your function this way as well. You can create a function which can do certain work for you, and then it can stop at the when it's needed. And that function is called the generator function. So if I now let's write a loop. Okay, I'm going to say for, let's call this sq. Okay, for x in sq, print x, and let's run this. So you see that this is we are writing a loop on a function now, and the function, every time we call it, it returns a value, because the for loop internally is calling the next on this. It's the same way you print a string. When you say for x in s, so for x in s, print x, in the same way you call for x in this generator function, print the next output. And the generator function is going to remember the previous, and it's going to print. So by using this yield, you can create a generator function which is going to return multiple times. So before I move forward, any questions with this?
So I can see there is a saving in memory, I think. So we don't calculate all the value one time. You call them when you need.
That is one reason. Yes, that is correct. Because if we don't want to store everything and in the memory, then we can create something like this. But more importantly, this is used when you want to return at specific intervals and remember the state information. If you were to do that by yourself, then you will have to use some kind of a stack or a queue to remember certain things where things are. Let's take an example. Suppose you have a list, okay, and the list is of some characters. Let's take this list. Okay, suppose it has A, B, and B, C, and let's say D, E, F. Suppose I tell you to print each character of this list. Okay, this problem is not very hard. Suppose each character of this list. If I just say for X in S, print X, then you will get A, B, C, D, E, F. So you'll have to write two for loops. It's not very hard, but I'm just demonstrating the use of generator function. But suppose you want to print the next character. So suppose I ask you to write a function that returns the next character that's present. So the first it should return A, then it should return B, then it should return C, then D, E, and then F in that way, not the whole items. Then I can write a generator functions. I can write, for example, def uh, letter, and suppose it takes in some kind of a sequence, and then it's going to say, okay, for word in sequence, something like this, and then for character in word, yield character. Suppose it's like this. So this letter of, let's say, S will return a generator object, and suppose you have chars equals to that, and you do next of chars. Now if you keep doing it, notice it will just keep generating the next character and it will remember its value. What I'm saying here is that for each word in the sequence and for each character in the word, for in this word, return the character. So this for loop is running and the generator function is keeping track of where this character currently is. So when we repeatedly run it, we get just the next character that we need. For example, consider this programming problem. I'll give you an example of a programming problem. Suppose you have to write a function. You have to write a program that compares the letters of the two lists. Suppose the first list is, let's say, A, B, C, D, E, and F, something like this. Second is, let's say, A, B, C, D, E, F. Suppose I ask you to check whether both the list contains the same characters in the same order. Right, then the answer is true. Yes, they contain the same characters in the same order. However, if you try to do the comparison just by writing the for loops and comparing this with this, then it will fail because these will not match. Now you can obviously join the whole list. This, if you join this, then it will become A, B, C, D, E, F. And if you join this, then it will become A, B, C, D, E, F. And you can compare that and it will give you the answer. But you might not have enough space to do that. This list might be very long. In that case, you can write a generator function and pass both the list to that generator function and just run a loop and compare the next character this way. So I'm going to give you a minute if you want to try this out yourself. And if you have any questions, you can ask me. And this is the example of the generator functions that we used. And since we're talking about generator functions, I'm going to talk about the last related topic that I want to discuss today. It's called generator expressions. Now, this is not function, but it's a related concept, so I want to club this right now. We talked about list comprehension expressions. So suppose you have a list, and let's say the list is, suppose let's write x for x in range 100. So this is your list. Now let's say you want to generate a list from this list. And actually take this example again. When you run this expression, this generates a list, right? So if this was, let's say, 10,000, then you will generate a list of size 10,000 like this, and this will be in the memory. There is another way you can do this, and that is that if you put, instead of a square bracket, you put round brackets. Now if you do that, then the list is not created immediately. Instead, this creates a generator expression. Right? So this is a generator expression. So nothing is now created in the memory. Okay, so just quickly, let's come here. Let's say you write a list comprehension expression, and then you say, okay, x for x in range 10,000. And let's say this is your memory. Then immediately this list is created in the memory with the letters from 0, 1, 2, and all the way to 10,000. So it occupies some space in your memory, right? Whereas if you put this x for x in range of 10,000, then a generator expression is created in your memory. This generator expression is only going to give you the next item that you want from it, and you can do whatever you want to do with it. So if I do next of L, this will give me 0, 1, 2, and it will keep going on. The generator expression will keep a track of where it is in this. So it will keep track of that. If the x is 5, then the next time it needs to turn 6. And when it's on 9999, the next number is 10,000. At that time, it will do the stop iteration. So let's just create, for example, a simple case of, let's say, 5. And then you do next of L, next of L, next of L. And now you come to 5 and stop iteration is thrown. So essentially, you know that you have reached the end of this generator expression. The advantage of generator expression is that it doesn't consume memory in one shot. Each time you're using constant amount of memory to get the next item. Right. So if you look about generator expressions again, so one of the thing is that no instant memory, although it is slightly slower compared to comprehensions. Now, if you were to do these two things, suppose you were to write this two expressions that 100, and if this was to generate 100 items versus you were to, let's say, create a generator expression, let's say expr equals to that, and you were to write like for x in expr print, for x in expr print x. If you were to do these two things, then this would run faster. The whole operation, this list comprehensions will run faster. But in many of these times, you will not worry about this speed. If the list is huge, if let's say a file is huge, then you want to create some kind of iterator that you want to can that which with which you can loop rather than store everything in the memory. But having said that, in the normal world situation, you will not run into the problem where you have to worry about the memory. Okay, so usually list comprehensions are fine. Even when you are even when you're dealing with uh, the whole of the novels, you are fine. So don't I mean you will not have to worry about the memory that much unless it's like a really really big program. So that's the generator expressions. If I run this, and this will be a they will create a generator expression. Any questions in this?
So when you mentioned you don't normally, in practical terms, need to worry about the memory or performance, then it's relatively nominal, the gains, or like within single digit percentage. I don't know if there's a rough ballpark to understand.
So the rough ballpark figure is that the list comprehensions generally will run twice as fast as the for loop. So that's the number.
Okay.
Now I don't know the exact mechanisms, but I know that list comprehension roughly run at the C speed because they are internally compiled
Mhm.
in C. That's what the logic says, but I've not really delved deep into that fact. So if let's say you were to create, let's say if you were to write something like this, suppose x equals to my list equals to this, and then for x in range of 10, my list dot append x, then my list becomes this. Or if you were to write x for x in range 10, so in these two expressions, these two situations that we did, the solution number 1 and the solution number 2, this one will run twice as fast compared to this one. And when you create the generator expressions, you are roughly in this area where you'll be writing a for loop on top of it to iterate. The saving is really in the uh, in the aspect of memory there.
Mhm.
Yeah. So if you're, let's say, like writing some kind of an automation in a company or something like that, where you're basically storing some information, then I mean you don't have to worry too much about the memory. It's all fine. But if you're dealing with huge amount of data, then you have to worry about this.
So it's not necessarily the generator; it's the for implementing the generator.
Yes.
Okay.
Once you get into the for loop, then
Gotcha.
it's yeah.
I mean, double is actually pretty significant in terms of performance if you're talking about speed, right?
Yeah, but I mean, even let's say for general purpose programs, right? For general purpose programs, this does not matter. But for high performance programs, yes, it does matter.
Mhm.
That's right. There are things that you can do. I mean, once we get into the algorithms and data structure class, I will talk about certain things that you can do just by just the creation of the list. There are certain very fast ways of creating list, and then there are certain very slow ways of creating list. And if you try to calculate the time of creating list, you will see a difference.
Okay. So if I understood this correctly, so the for with the generator is double the list comprehension plus there's no memory, so constant space pretty much, or something on in that magnitude.
No, that's
Right.
correct. That's correct. That's correct. So it
Oh.
will run half the speed, but low memory.
Okay.
Versus list comprehensions are going to consume more memory, but double the speed.
Okay. Gotcha. So that's a trade-off.
That's a trade-off, yes.
Right. Okay. I mean, that's important for algorithms.
That's important for algorithms, but that's important for algorithms in a different way. I mean, we can talk about it as an offline topic, but
Okay.
if something is linear time, then it is still linear time, whether it's slow
Right.
execution or fast execution. So
Gotcha.
it does not matter that way. The asymptotic growth is still the same.
Gotcha.
Yeah. So that's all I had for today. Okay, and I'm gonna end the session today early as well because I have something at 8. I need to like get ready for that. So if you have any questions, go ahead, you can ask me, or else I'm
So-
going to stop the session.